Mr. Tarou, in part 2 of looking at trigonometric integrals involving powers of secant and tangent, we're going to be doing 5 examples. Now, in the description of this lesson, not only will you find timestamps to those 5 examples if you want to skip ahead, you don't need to hear this entire lesson, you'll also find a link to part 1 where I talked about trigonometric integrals involving powers of sine and cosine. Now, the derivative of sine is cosine, and the derivative of cosine is negative sine. So, you go right from one trig function to the other, regardless of which trig function you start with, sine or cosine. So those problems tended to be fairly straightforward. Of course, in calculus, even stuff that maybe seems straightforward at first will be a little bit confusing for some of us. And when you deal with secant and tangent, the derivative of tangent is secant squared, and the derivative of secant is secant of x times tangent of x. So that's a little bit of an issue there, where the derivative of secant has in its derivative secant and tangent, will allow us with some of these problems to have a choice in how we start our problem. And we're going to be talking about that in the third example. I think it's a third or maybe second example, where we're going to do that example 2 different ways. And we're going to get 2 answers that look completely different. But when you graph them, you will have the exact same graph, showing you that they're equivalent. And depending on the approach you want to go through, you will find that one way is easier than another, and the choice that you make is going to be dependent on a particular problem you're doing in your homework. So let's get to those 5 examples, shall we? Here we have the guidelines for doing these trigonometric integrals, which you will probably find in your textbook. And we're going to try and make sense of these and then work through and clarify what's going on with our 5 examples. If the power of the secant is even and positive, say the secant squared factor and convert the remaining factors to tangents, expand, and integrate. So we have the secant raised to a 2k power of x and the tangent of x raised to an n power dx. Here we have this exponent of 2k. Anytime you take a number and you double it, of course you get an even answer. So we're looking at that even power on our factor, which is secant. We're going to pull one of those out, so we see a secant squared raised to the k minus 1 power, and a secant squared over here. Well, of course, power to power means that this would be 2k minus 2. Here we have a secant squared. When you multiply like bases, you add the exponents, and 2k minus 2 plus 2 gets us back to that original secant with the even power. I'm just trying to explain a little bit what's going on in this expansion notation that you see in your textbook. Now we're going to take the secant squared with Pythagorean identity, which is of course 1 plus tangent squared of x is equal to secant squared of x, and we're going to do the expansion and have a bunch. It depends on how you write your problem. I'm going to give each of the terms their own integral notation, and what we'll eventually see is we'll have powers of tangent, and then that u prime or that du here, our tangent derivative of tangent is equal to secant squared of x. And that'll allow us to go through the integral using the power rule. If the power of the tangent is odd and positive, save a secant tangent factor and convert the remaining factors to secants, expand, and integrate. We have that notation over here. If there are no secant factors and the power of tangent is even and positive, convert a tangent squared factor to a secant squared factor, so you have that du or that u prime, and expand and repeat if needed. This repetition here, I'm trying, I want to make up my own examples, not just use the textbook examples or the examples in the textbooks, not to have any kind of copyright issues with the books. Plus, why do something that's in our textbook, because it'll be there already. And this guideline about there are no secant factors and the power of tangent is even and positive. My example is going to have no secant factors and a power on tangent which is odd, but we're still going to basically go through this process. It's just we'll have an extra factor of tangent, which we'll have to deal with just by using the basic integration rule for tangent, that the integral of tangent is equal to negative natural log of the absolute value of cosine. If the integral is in the form of secant raised to some power, secant of x raised to some power m dx, where m is odd and positive, use integration by parts. That'll be our last example. We'll just do a basic one. We're going to integrate secant of x cubed. And then if all else fails, try converting your integrand into sine and cosine, kind of like when you were doing trig proofs and you all else failed to try and get the two sides of the identity to match. You would go into sort of the parent functions for the trig functions, which is sine and cosine, and see what could happen there. We're not going to do any examples like this of our 5 examples. We're not going to need to do this last step. We're going to save that for part 3, our last lesson, helping you work with these trig identities, or excuse me, these trigonometric integrals that have some kind of powers of sine, cosine, secant, cosecant. And what we're going to learn here in this lesson, dealing with powers of secant and tangent, of course, are going to apply to integrands that have powers of cosecant and cotangent, because the derivative rules worked very, very similar. The derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared, and of course we should know what the derivative of secant and the derivative of cosecant is, and see how similar those derivative rules are. So let's get on to our first example right now. So starting off with our simplest examples in the beginning and working through an increase in the difficulty through our examples, we have example number 1, the indefinite integral of secant of 4x raised to the 6th power dx. Now if it was just integrating secant of 4x, we could use our basic integration rule for secant and write the answer. Just about. We can have an inside function there of 4x, but because the secant function is inside the power, then the secant is inside the power rule, the power of 6, and we would need a du. We would need to be able to have a derivative of that inside function. So what we want to do is we want to rewrite that integral to have a tangent function and a secant function. And with this being an even power, we can pull out a secant squared, be left with a secant to the 4th power, and then, using that first, one of those Pythagorean identities, 1 plus tangent squared is equal to secant squared, convert those remaining 4 powers of secant into tangents, and then we'd have that inside function for the power will be the tangent, and that du or u prime would be the secant squared that we're going to leave out. So we have the indefinite integral of secant of 4x to the 4th power times secant of 4x squared dx, and I always like to wrap my angles in a set of parentheses just to really make that notation as clear as possible. So this is going to be our du, this is going to be our u prime, this is going to be the derivative of the inside function, that function inside the power, which we're going to convert into tangent. So the Pythagorean identities, of course, are not for trig functions in powers of 3 or 4 or 5 or 6 or whatever. It's powers of 2. So this is going to get rewritten as the indefinite integral of secant squared of 4x, then raised to a 2nd power, times secant squared of 4x dx. 1 plus tangent squared is equal to secant squared, so we have the indefinite integral of 1 plus tangent squared of 4x raised to the 2nd power times secant squared of 4x dx. Now for just speed of the video and make this as efficient as possible and not quite so boring for you to watch, I'm going to step off. We're going to take this binomial, raise it to a 2nd power, have a trinomial, distribute that secant squared of 4x into each of those 3 terms. And I'm going to give each of those terms a root integral just for, maximum clarity of my work. You may find that you don't need to do that as you practice these problems more and more. Maybe you want to streamline your work a little bit, but I'm going to break this down into as small as I can, as small of steps as I possibly can. So there we go. Of course, we have that binomial expanded. Again, like I said, multiplying that secant of 4x squared dx through each of these 3 terms, setting up a separate integral for each of those integrands. And the integral of secant squared, of course, is going to be tangent. And just completing the chain rule here so that we can recognize that pattern and then just integrate using the power rule. We've got the derivative of tangent of 4x is going to be 4 times secant squared of 4x, because of course you have to take the derivative of that inside function, which is going to be 4. And then I'm balancing out those multiplications of 4 with divisions of 4 in each of those terms, and then finishing up, of course, don't forget your constant of integration, and there is our final answer. Now for our second example, it's going to follow that third guideline where it said if we had no factors of secant and we had a tangent just simply raised to an even power, pull one out, a power of 2 of those out, convert to secant, and so on, repeat if necessary. We're going to do that, except it's going to have an odd power, and that's just going to leave us, like I said, an extra power of or factor of tangent when we're done, and we'll just integrate that tangent with a basic integration rule. So we have started off example 2, the indefinite integral of tangent of x raised to the 7th power dx. Now, just to be different from problems that are in the textbook that I teach from, I've got a single angle and I have a power of 7, which means that whole idea of repeat if necessary is going to take a few repetitions. More than likely your book probably has something like a tangent of some 3x or 5x or some kind of multiple angle, and then it's just raised to the 5th power, so you'll have to repeat this process twice. We're going to have to repeat it 3 times. But the whole point of taking a tangent squared factor out of that whatever power of tangent that you have in your problem is so that you can use the Pythagorean identity, of course, and get a secant squared factor into your integrand so that you can have a derivative of your inside function, have a derivative of that tangent, which is secant squared. So far, we're here and we have the indefinite integral of tangent of x to the 5th power times secant squared of x dx. Well, this is our u, tangent of x, and our du is the secant squared of x squared dx. So we're just going to use the power rule to integrate this first integral, and then continue the expansion, again, 2 more times, with this indefinite integral of the tangent of the 5th power. See, we're breaking this down in steps of 2. So I'm going to step off, reveal the rest of this example till we get to the very end, and we have to integrate that last odd power of tangent that we have, and remember that the indefinite integral of tangent of x is negative natural log of the absolute value of x. Bam! Alrighty, example number 3, we're going to find the indefinite integral of the tangent of 3x raised to the 5th power times the secant of 3x raised to the 4th power dx. Now, to remind us of what those guidelines said, it says if the power of the secant is even and positive, check, save a secant squared factor and convert the remaining factors to tangents and expand and integrate. If the power of the tangent is odd and positive, check. Then save a secant tangent factor and convert the remaining factors to secant, expand, and integrate. Now, we haven't gone to powers of secant yet. Remembering the derivative of secant is secant tangent. So we're going to do basically we have a problem, an integrand that follows both of those guidelines. Now we're going to do this again first, going into powers of secant and finish the problem, and then we're going to look at how we could go the other way, noticing that the secant factor has an even power as well. So we're going to take this tangent, we're going to pull one of these tangents out because it noted if the power of the tangent is odd, save a secant tangent factor. Well, let's focus on getting that extra secant out there in a second and just get our factor of tangent, get it into some powers of secant. So we're going to write this as the indefinite integral of tangent of 3x times tangent to the, not squared, but 4th power of 3x times secant of 3x raised to the 4th power dx. Now, really, I'm gonna go to the line I was just about to write anyway and write this as tangent squared squared. To save a line of work, let's just do this. Excellent. Now, Pythagorean identity, tangent squared of an angle is equal to secant squared of that same angle minus 1. And I'm going to step off. We're going to expand that binomial, distribute the tangent and the secant to the fourth power to each of those terms, and come right back. So we have that binomial expanded, multiplied the tangent of 3x and the secant of 3x to the fourth power through each of those three terms. Now, I'm going to go ahead and show how we're saving that secant tangent factor, because now we see we have a secant raised to a high power in each of these three terms, and the derivative of secant is secant tangent. So we're going to pull one of these powers of secant out, and I'm going to also put the powers first just so we have the du at the end, and we're going to have the indefinite integral of secant to the 7th power, or secant of 3x to the 7th power. Now we're going to have that secant tangent, and inside of our trig function we have a 3x. Well, the derivative of 3x is 3. So I'm also going to, for purposes of completing that chain rule, write this as 3 times secant of 3x tangent of 3x dx. And to balance that now, that multiplication of 3 for the derivative of that inside function of 3x, we're going to balance that, of course, with a coefficient or factor of 1/3, or division of 3. And I'm going to do that with each of these three terms and just finish up the problem. And then we'll look at this another way, where instead of putting this into powers of secant, we're going to put it into powers of tangent, pulling out a secant squared, or secant of 3x squared, and show you why, and talk about why that version of this problem is going to be less work. Bam! And there is our final answer, all in powers of secant. Now what we're going to do is, we're going to go and use the other guideline, which is not the guideline where if the power on tangent is odd, but if the power of secant is even, and rework this problem in terms of powers of tangent instead of powers of secant like we did in this particular example. And it is going to be less work the second way we do the problem. And it probably is a little bit less work to go into powers of tangent, just because the derivative of tangent is secant squared, as opposed to having the derivative of secant be secant and tangent, just being like a little bit less writing. But the main purpose, or the main reason why the second version of the solution is going to be less work is because we have a power of 4, which is closer to and easier to get down into a power of 2 using that Pythagorean identity, and the fact that the derivative of tangent is secant squared. We have a power of 2 in that derivative, as opposed to the derivative of secant, which is secant and tangent. Not only do we have two factors, but we have powers of 1 as opposed to powers of 5 or 4 or 2. So let's break this off, and hopefully you can see the difference between the yellow and white chalk, and I think I can fit the whole second version of the solution over here. We're going to write this as the indefinite integral of tangent to the 5th power, or the tangent of 3x to the 5th power, times the secant of 3x squared times secant of 3x squared dx. And like you saw me do in the first two examples, I'm going to step off just to make sure this is as neat as possible, and to speed up the video a little bit. We're going to take this secant squared, write it as 1 plus tangent squared, and basically now finish this similar to examples 1 and 2, and you'll see that at least in this example, going into powers of tangent allows us to have, or more quickly, solve this problem. Bam! And there is a perfect example of how That question can have two solutions that look so different, not only in the amount of work that it takes to complete those problems, but if you put your calculator in radian mode and type in this equation, y equals all of this, and you can not worry about the plus c there, and you type in y is equal to 1/18 tangent of 3x to the 6th power plus 1 over 24 tangent of 3x to the 8th power, you will get, as different as these equations look, the exact same graph. Now let's move on to example number 4, which is going to be much quicker than example number 3, and we'll only do it once. And for example 4, we have the indefinite integral of tangent of x cubed times secant of x cubed dx. And a very similar problem to the previous example. It's just that this one you don't have an option, I don't think a good option of how to do this. You just want to pay attention to the fact that the tangent of x is got an odd power to it. So we're going to save that factor of secant of x, tangent of x, and put this into powers of secant. And that is all we have to do with that problem. Taking out our factor of secant tangent, now we have the tangent of x being squared using the Pythagorean theorem to convert that into sine squared minus 1, distributing the secant squared x times secant of x, tangent of x dx through those parentheses, giving each of those terms their own integral notation, and we have our u, which is secant of x, and du being secant of x, tangent of x dx. Now, our last example is just going to the fourth guideline, which said that if secant has an odd power, to integrate using integration by parts. And we're just going to do a simple integration, indefinite integral of secant of x cubed dx. It's our last example. Example number 5, we have the indefinite integral of secant of x cubed dx. Now this is a pretty innocent looking example. Looks very similar to the one we did earlier, which was just having a factor of tangent being raised to an odd power, and you saw that that really worked out pretty easily, except for the fact they gave it a, I think what was it, a 7th power, and had to do a couple of repetitions of the same type of process, but it was not a big deal. Here, it's going to be a little bit more of a big deal. If you try and write this as secant squared x times secant of x, and then take your secant squared and write it as 1 plus tangent squared x, you're going to kind of just go in a circle and get right back to where you started from. And we're going to have a little bit of that issue as well going through the integration by parts. You'll see something come up that would have shown up in that lesson when you were first learning integration by parts, how sometimes you had to go through it multiple times and end up through the process of going through integration by parts getting one of your terms that matches the original problem, and well, you're going to see that happen here. So our integration by parts is going to be the indefinite integral of u dv is equal to, except that's not a u, or that I wrote a u, not a v. So let's try that again. The indefinite integral of u dv is equal to uv minus the indefinite integral of v du. Okay, so we want to, with indefinite integration by parts, look for a factor, the most complicated factor that can be integrated using a basic integration rule. Well, right now we're just looking at the indefinite integral of secant of x cubed. So we are going to split this up into two parts like I mentioned just a second ago, and say that this is equal to the indefinite integral of secant of x times secant squared x dx. And this is the most complicated factor that can be integrated using a basic integration rule. So we're going to let dv equal secant squared x dx. That means that v is the indefinite integral of secant squared x dx. And of course, that's going to be tangent. Okay, now we got our v, we have our dv. We need to know what u is, and the u is just whatever factor we haven't used yet in our integrand, which is going to be secant. So u is equal to the secant of x, and du is going to be the derivative of secant as secant tangent of x dx. And so now we're just going to plug all this into our integration by parts formula. So we have u and v, so we have secant of x tangent of x. I guess I'll write that over here. Minus the indefinite integral of v, which we have here is tangent of x du, and our du is secant of x tangent of x dx. Okay, now, fantastic. Here, well, we have a lot going on here. If we look at secant of x as being ru, then du would be secant of x tangent of x, and we don't have another secant factor in here. The derivative of tangent is secant squared, so it seems like we're not going to be able to easily work with this integrand or integrate this expression. So we are going to put the tangents together and write that we have secant of x. Okay, but whatever, same issue we had here. We don't have a good u and du in here, so we're going to go ahead and convert tangent squared x into secant squared of x minus 1. Distribute that secant of x. Okay, now I'm giving each of these terms their own integral notation. Secant of x times secant of x, of course, is secant cubed x, and you just saw me do this in my previous examples as well. And we have that negative there. Now I'm going to do secant of x times negative 1, which is negative secant of x dx, but then that negative's coming over here, so we have plus the indefinite integral of secant of x dx. Now, at this point, see, we started off trying to integrate the indefinite integral of secant x cubed, and we have another secant x cubed, and we had this happen when we first went through the process of learning how to work with integration by parts. Sometimes we kind of circle back to our original integrand. So let me go ahead here, and the indefinite integral of secant of x is the natural log of the absolute value of secant of x plus tangent of x. Get that plus c in there. We still have an indefinite integral in here, but what I'm going to do is add that to the other side. And let's go ahead and do that at the same time. The indefinite integral of secant of x is the natural log of secant of x plus tangent of x. I'm going to add both sides of this equation by the indefinite integral of secant of x cubed. So 1 plus 1 is going to be 2. Stretch out my space in there a little bit. And now I can divide both sides by 2 and get the indefinite integral of the secant of cubed x dx is equal to 1/2 secant of x tangent of x plus 1/2 the natural log of the absolute value of the secant of x plus tangent of x plus, and you know, c, an unknown constant divided by 2 is just yet another unknown constant, you know, whatever, subscriptive 1, or just leave it as another unknown constant of integration. Let me double check, make sure I didn't do something silly. And we've got, there we go, 1/2 secant tangent plus 1/2 natural log. Excellent. And that is the end of my last example and the end of this particular lesson. I'm Mr. Tarrou. Bam! Go do your homework. Or if you want to see even more examples, I'll have a part 3 coming up, and I'll put a link to that lesson in the description just as soon as it's done.